Hello, welcome to this video. The content will be my view, Peppe's view on Bellman equation. So, let's start from this idea. We have a series of states. For example, we start from S1, and then we navigate, we evolve into S2, and then S3, and then so on and so forth. And it's a Markov chain process. So the next state, S2, let's say, is only function of the previous state. So S2 is only function of S1, S3 is just a function of X2, and so on and so forth. Now, the idea is that you can take action that will bring you from a certain state Sj into a new state Sj plus 1. And you do that by taking an action. So if we make an example, we are in state S1, then we are taking the action A1, a certain thing that we do, that we decide to do out of our own free will, and we end up in S2. Finally, another bit of information that we want to add in this picture is that for each action that we take given a certain state, we get a reward and or a punishment from the environment, which is this external thing that surrounds us and basically repays us for what we do or punishes us for what we do. So the picture gets improved by this addition of the reward. So basically, we are in S1, then we look around, we see the world, let's say, we decide that we want to take a certain action, in this case A1, we end up in S2, and as a result of us taking the action A1, given the state that we were in, so as a result of us making A1 and the state that we were in, so S1, we get a reward, which can be positive or negative, so it's a reward or a punishment, which I called R1 in this little graph here. And then we do this over and over again. So our process looks like this. So we have S1, again we start from S1, then we take an action, we go to S2, we get a reward or a punishment. Then from S2 we take another action, A2, we go to S3 and we get a reward or a punishment, and so on and so forth. Now, what we want to do now is knowing what to do at each state St. Let's say that T is an index that reflects the time step that we are in at the given moment. So we want to do at each state what should be the right action to take in order to maximize our reward. So we want to know what is called a policy, this pi function of St, which is basically a mapping from the state St here to the action At. Basically, it means that for each state St, we know what is the best action to take. And so pi is our policy. It's just a mapping from the state to the action, and this works at every time step t, because at every time step t, we want to know what to do. That's a bit the idea. Then we introduce another function, which is called capital R. It is the reward function, and it's a function of the state that we are in at the moment. So it's a function of St, state t, and action t, and gives us small r t. So at each time step, knowing the action that we take and the state that we are in, we know also what would be the reward for that given time step. And so, given that A of t is the policy given the state St, we can rewrite everything, the reward function, as a function of the state itself and the policy function of the given time step St, of the given state at the time step t. What do we want to do here is to maximize the reward, or what's called the utility function. So we have this v value value function, given pi, so that's the pi over here, given our policy, okay, and given our starting state s of 0. That's the starting point. So we want to maximize what is called the expected utility, so this v pi of the given state s0. Well, what's this expected utility? So imagine like this. Say that you are at a certain time step t, you take an action, so you are going to get a reward. That would be the reward that you get at time t for the simple fact that you took an action. So that's the reward at time step t. This will bring you to another state, if you want, st plus 1. So you have to sum over all the time step that you have, from time step 0 to the maximal horizon that you can have. I called it h in this formula here. So you have to sum over all the time step that you can possibly have. And what do you have to sum? You have to sum the rewards that you get given the time step t and given the state that you are in at the time step t. And then this gets multiplied by the probability that you end up at time t at that precise state st. So that's why you need to multiply the reward by the probability of being in that state t, because maybe it's an impossible state to be in if you start from s0 and if you apply the policy pi. So you do reward times the probability of ending up at that state. And then the last thing that you have to do is to sum up over all the possible states st. So that's the idea of this other sum here. And that's the utility that you expect. So if you want how much you expect to gain at the end of this process. You want to maximize that, but you can introduce also the concept of inflation. So you can multiply the rewards that you get at every time step by a certain discount factor, which is this gamma to the power of t, this thing here. And the meaning of that is that basically it's not the same to gain $1 now or to gain $1 in 10 years, because there is the inflation. And so you have to discount the fact that basically $1 values more now at the present moment rather than in 10 years. You expect a discount factor. So you put that gamma, which is less than 1, it's a factor less than 1, maybe 0.9, 0.99, something like this, and you exponentiate it by the time step t. And you call it discounted cumulative reward. So our goal in all of this picture is to find the best policy that I called pi star that is optimal. And definition of optimal means that v using pi star, so our expected discounted cumulative reward, if you want, so our expected revenues given the policy pi star is greater or equal than our expected revenues for all other possible policies pi. That's the definition of optimal. How do we do that? How do we find pi star? Well, there are several techniques. I listed three of them here. So we have value iteration, policy iteration, and search iterations, search techniques. But I'm gonna describe only value iteration here, only that technique. And it's basically based on dynamic programming going backwards. Let me explain you what I mean. So, as I said, we go backwards. So we start from the very last time step t. Well, it's our end game. There is nothing else to do. This is the last time step possible. The game is over next in the next step. So what do we do? The best thing that we can do is maximizing the reward for that last time step, because it's the last time step. So the best action that we can take is the action that maximizes the rewards for that very last time step that remains us. And basically, you see this in all possible games. If the game is finishing, so there are a few minutes left, well, the way the teams start to play at that moment is different than what they did during the game. So at the very last moments, they start playing differently because they have to do everything they can to win the game. And that's why that's the idea here. You maximize the action because it's the last thing that you can do. So you want to maximize the action and maximize the reward that you get at the very last time step. That's very simple. Okay, then let's go two time steps back. So what would be the value for S, so the state at h-1, so not at the horizon, one step before? Well, you have two components now. You want to maximize two things, or the sum of two things. You want to maximize the sum of the reward that you expect to gain right now, but that's not the end game. So you still have hope, if you want, that in the future things are gonna be better. So you don't really want to take the best possible action now, because maybe that's not the optimal thing to do, given that you have another time step to go. So you don't want to maximize only the reward now, the immediate reward. You want to maximize the sum of the immediate reward that you get by doing a certain action, A of h-1, I called it, plus the reward that you are gonna get in the next state. And that's the idea of this plus gamma. So you discount it by gamma because you have to wait. You don't get the reward now, you have to wait. Then you could get this value of sh if you do a certain thing, and then you multiply, as we did before, for the probability of ending up in that precise sh, given the fact that we took the action of h-1. That's what you do to maximize the value at time step, not the last one, the previous to last. And the good thing about this is that we have already v of sh because we imported from the previous calculation that we did. That's why I put this blue arrow here pointing to v of sh. We already computed v of sh at the previous computation step, so we can insert it now, and that's why we are going backwards. And same thing, what's the value of sh-2, so 2 steps before the end of the game? Well, you do the same thing. You have to maximize the sum of what you can get now, plus you discount all your future revenues. And the same thing as before, and again, we are going backwards. We have already computed v of sh-1, so we insert it back, and so on and so forth. So if we put everything together, we have the famous Bellman equation, which basically generalizes what we said before. So for each time step t, v of the state st, the expected value, is the maximal over all the action that you can take at that time step. And the idea is that for every time step, you maximize the immediate reward, plus you discount all your future rewards. That's the idea. And then we did all of this because we want to know the policy. So we want to know which action should we take at every time step. So if we have the expected value, so we have maximized the value of our revenues, then we take the argmax, so the argument that maximizes the revenues, and we get h star of t, so our optimal action to be taken at each time step t. So, as at each time step t, I know what to do, I know my action to be taken at a time step t, I know my policy, and I know what to do. That's a bit what I wanted to say about the Bellman equation. I hope you enjoyed this video. If you liked it, please hit the subscribe button. Drop me a comment down the video if you want to share your thoughts with me. And till next time, bye bye.